All right, make sure you have a calculator for today and open up to 301. All right, so yesterday we were kind of exploring particle motion and different properties, relationships, terminologies. We wrote connections down in a chart. We wrote down some very important and specific characteristics or properties of particle motion that kind of have misconceptions that we've got to make sure that we're okay with. And then today we're just going to take a look at a bunch of examples that apply all these relationships and terminologies and connections together. So I'm hoping that today's kind of like the sink-in day, if it hasn't happened yet. I'm hoping by going over some examples we start to see how like position, velocity, and acceleration are all related together. So at the bottom, we're going to have this function that represents the velocity of a particle. So sometimes they'll list it as v of t. Sometimes they'll say like p prime, the derivative of position. So we have to make sure that we're okay with the connections or how the function is represented, okay, by the way that they name it. So they tell us that this is velocity and we only want time greater than or equal to 0. So it's not like we're looking in the past of how this particle was moving. We're just looking at this moment in the future. We have units of measure, minutes, and inches per minute. So that's one thing about this particle motion, we're always going to have units. More often than not, we'll always have units. So answer the following questions. Find the values of v of 3 and v prime of 3. Can we rename v prime of 3 if it's saying the derivative of velocity? A for acceleration. Okay, so you can rename it if you want to, if that helps you understand what the number actually means or what the function is telling you. You can rename it a different letter. All right, so how do we want to go about finding the velocity at 3 and essentially the acceleration at 3? With the information that they provide to us.
I'm going to plug 3 in.
Okay, well let's do that for this one. V of 3, so they give us the V function. Let's go ahead and plug in 3. So we'll have 5 times 7 squared. So 5 times 49, 245. Can we put a unit on that number?
Yes.
What might that be?
I don't know.
All right, so this number 245 came from the velocity function, so it needs a velocity unit.
Inches per minute.
Inches per minute. Looks good. All right, how do you want to find the acceleration at 3? You got to find the derivative. Okay, now can we think about how we would do it by hand? Find the derivative of this function?
So you do the calculator.
Okay, we're eventually going to do the calculator. Okay, that's why I wanted you to have one. But if you look at it, we would have a product rule, but also a chain rule in there because of the power of 2. Okay, but if we have a calculator, we should be able to do this one by hand. I'm going to tell you right now. We should be able to do it by hand. But we have a calculator, so we'll use that to our advantage. Do you remember how to use the derivative command on our calculator? What buttons? Math. Number 8. All right, first box is always x. Middle box is always the function you want to take the derivative of. So we're going to type in our velocity function. And then the last box is always the value we want to plug in to the derivative. So in this case, that'd be 3. And if we round that to 4 decimal places, it'll be 119. All right, so 119. Can we put units? This is an acceleration value, so we need acceleration units.
Inches per minute squared.
Inches per minute squared. Good. Okay, so with these two pieces of information, okay, we're going to try to describe the speed of the particle. Okay, now if you look at, I think it was number 3 and number 4 from yesterday in the 5 commandments, the 5 important things with particle motion, those dealt with speed. So we got to try to figure out, is our speed increasing? Is our speed decreasing? What is the case based off of these values? If we look at them, since velocity is positive, we know we're moving in a positive direction, so either right or up. And since acceleration is positive, we're accelerating either to the right or up. So if you're moving in a positive direction and you're accelerating in the same positive direction, what's going to happen to your speed?
Increase.
It's going to increase. Okay, so speed is increasing at t equals 3 because velocity and acceleration have the same sign. You're moving in a certain direction and you're accelerating in the same direction, so the particle or the object is going to speed up. It's going to increase, move faster. All right, part B. On which intervals is the particle moving to the left, to the right? Show your analysis and justify your answer. How can we start to determine in which direction a particle is moving? What do we need to analyze?
Sine.
The sign of what?
E velocity.
Sign of velocity. Okay. We mentioned yesterday how velocity tells us two things, speed and direction. So if we want to figure out if we're moving left or right, we got to analyze that sign of velocity. So velocity is already given to us. We got to figure out where's it negative, where's it positive. So setting up a sign chart with our pluses and minuses might be beneficial. We got to first figure out, though, where velocity is 0, because we can kind of use those as our barriers, essentially kind of our critical points if you think about them that way. So if we set velocity equal to 0, can we find those spots? T equals -2 and -4. So these are two places where we don't have a velocity. Okay, our position is not changing. We're kind of stationary for a moment. How can we figure out where we're going left, where we're going right? A sign chart. Okay, so the question is, what do we want to set up as our intervals? Are we going to do negative infinity to -4, -4 to -2, -2 to infinity?
Yep.
No. Yeah. Actually,
Maybe?
I don't know. It says T is.
That's what we did for functions, right? Because functions can go on forever. But now that we have a specific scenario, okay, meaning behind a function, they might be restricted. Notice how the time has to be greater than or equal to 0. So if 0 has to be our beginning point, we'll never include -4, -2, right? Because those are less than 0. So our ending interval would just be infinity. So even though we found spots where the particle might change direction, notice how it happened in the past, okay, because we're only focusing like at this moment in time and in the future. So we don't really have to include those in this case. So we really have to pick any number we want between 0 and infinity and plug it into our velocity. So if you plugged in any positive number into velocity, would it be positive or negative? Positive. Okay, so show your analysis, justify your work. The particle never moves left because v of t is never negative. It may have moved left in the past, but we're not really concerned with that because we want our t to be greater than 0. So we answered that question. They also want to know, when does it move right? So the particle always moves right because velocity is always positive. All right, so a little bit different. Our sign charts, we're used to having multiple intervals, but now that we're dealing with a particular interval, okay, time greater than 0, time greater than 5, whatever it might be, we have to make sure that we take that into consideration, okay, for our intervals themselves. All right, so far so good. I like it. Let's try a previous AP free response example, okay, where they're giving us a chart and a table to kind of analyze. So this is an oldie but a goodie, 1998. The graph of velocity, feet per second, so they give us units, of a car traveling on a straight road, so we'll assume left and right. Time 0 to 50 is shown below. The table of values for v of t at 5-second intervals is also shown to the right. So it's nice that they give us a graph because that's a good visual, but notice how some of the points on this graph might not be known. For instance, this point, this one, and this one don't happen at a crosshair or a tick mark, so maybe those are listed in this table. So the table just adds more value to the graph because we have some specific numbers. All right, let's try the first one. Determine what interval of time the acceleration of the car is positive. Give a reason for your answer. Basically, justify your answer if you want to bring that into consideration. So, if we want acceleration to be positive, notice how they give us velocity information, though. So, can we think about perhaps what our justification should be first? Can we make that connection and then we'll go back and try to figure out when that happens? What does velocity have to do in order for acceleration to be positive? Increase. Okay, if velocity is increasing, its slope, aka acceleration, is positive. Okay, we have those connections between derivatives and originals. We're just throwing in acceleration, velocity, and position as words. So based off of either the graph or the table, can we figure out where velocity is increasing? What do you think? The 0 to 35? I'm looking at the graph. Okay, 0 to 35 we're increasing, and then 45 to 50. You have that another little interval right there. Looks good. All right, part B. Find the average acceleration of the car from 0 to 50. Indicate units of measure. Average acceleration, aka average rate of change. How can we use velocity to figure out an average acceleration? Can we kind of describe in words, perhaps, what we should be calculating mathematically? If it's an average? Slope between 2 points. Okay, now if it's the average acceleration, it's the slope between 2 points on which function? The slope of what gives you acceleration? the slope of velocity, okay? It's the rate of change of velocity. So we want the slope between 2 points on velocity, and that's going to represent the average acceleration. So our interval is from 0 to 50, so we basically want the slope between those 2 points. Now, if you look at the graph, 0, 0, basically we have that available. But at 50, graphically, we might not know what that point is. So that's why they give us the table to make sure that we have that information exactly. So we're going to use 0, 0, and then 50, 72. We're going to calculate the slope between those 2 points. So we'll do change in y's over change in respective x's. All right, 72 over 50. You can leave it like that. You can simplify it. If you want to type it into your calculator and get a decimal, you can do that too. Okay, 1.44. Now they also want us to do units of measure. So if this number is representing average acceleration, this is an acceleration value. So we need an acceleration unit. Feet per second squared. Good. We did okay? I'll take the silence as yes. Okay. Find one approximation for the acceleration of the car at, okay, notice the wording, at time 40. So we want the acceleration at an instant, aka instantaneous rate of change. So show the computations you use to get your answer, indicate units of measure. All right, so acceleration at an instant, this would be the slope at 1 point on velocity. So graphically, let's see, if we were to go to 40 and draw a tangent line, we're going to try to approximate the slope of that tangent line. Now it says find one approximation, so there might be more than one answer, more than one way you can approximate this. Can we kind of brainstorm how we might be able to find at least one approximation? What do you think?
Use the slope of like a point that's before it and point that's after.
Okay, so instead of, I mean, I guess this would work. It says find one approximation. So if you tried to calculate the slope of that tangent line, I guess that would be an approximation. How good it is up for debate because there is some error within that. So to get a little bit more accurate, maybe we'll pick a point before it and after it. So graphically, we can use the point at 35 and the point at 45. Now on the table, we might be a little bit more accurate with those. So let's do change in y's over change in respective x's. Negative 21 over 10. So negative 2.1 as a decimal. Can we throw units on it? This is another acceleration, right? It's the acceleration at a point. Okay, so it still has the same units. Looking good. All right, last one. Is the speed of the car increasing or decreasing at time 40? Okay, justify your answer. What do you think we need to find or figure out? How can we determine if speed is increasing or decreasing?
The slope is becoming negative.
Say it again?
The slope is negative.
The slope. Okay, so at time 40, we know the slope is negative. So the slope of velocity is negative. That would mean acceleration is negative. So acceleration at 40 is negative. Okay, that's actually what we did in part C, right? Didn't we find an approximation for the acceleration at 40? Negative 2.1. So we know we're accelerating in a negative direction. Is that enough, though? if we're accelerating to the left and moving to the left, we're accelerating and moving in the same direction, so we know we're going to speed up. But if we're accelerating to the left and moving to the right, those are opposite directions, so we know we're going to slow down. It's like opposite forces, okay, it kind of slows something down. So we got to figure out which direction we're moving. And in order to figure that out, we got to know the velocity at 40, because velocity tells us direction as well as speed. So what's the velocity at 40? Positive, right? Looking at the table or the graph, it's above the x-axis. We have a value of 75. So if we are accelerating to the left but moving to the right, that's pulling us in opposite directions, so we're going to slow down. Okay, our speed is decreasing. So speed is decreasing because acceleration and velocity have opposite signs. Okay, this was kind of the misconception that I tried to hit yesterday, but I think the bell rang before I actually had time to do it. We are used to understanding that if we are accelerating negatively, okay, decelerating, that means we're slowing down. And we're used to that because in our driving instance, our direction's always positive. Okay, if you look at your speedometer, isn't it always positive numbers? That's your speed, okay, velocity, direction. So just because you're decelerating doesn't mean you're slowing down. You also have to take a look in which direction you're moving to help you make that connection. So we actually have two things that we need to check. Okay, well, we might see another one of those in another question. All right, not too bad. Let's take a look at another one. Another oldie but goodie. Yeah. Yes. 2000. Two runners, A and B, run on a straight path, 0 to 10 seconds. The graph below consists of two line segments, shows the velocity in meters per second of runner A. And we have velocity in meters per second of runner B given by this equation. Okay, so we actually have two different pieces here. They're not related. So this equation does not produce this graph. I hope we realize that anyway, but we have two different pieces here. So let's see, find the velocity of runner A and the velocity of runner B at time 2, indicate units of measure. All right. Velocity at time 2. How do you want to approach either one of those? The graph is runner A information, the equation is runner B information. I see pencils moving, which are good, but I want to know what we're doing. I know we rely on Addison, but he went to the bathroom. Let's see, I'll do B. Velocity function. Okay, we're trying to find velocity at 2. So if we plug in 2 into the equation, 24 times 2, 48. 4 plus 3 on the bottom, 48 divided by 7. I'll leave it like that. Can we put units there? Meters per second. Okay. Looks good. What about the velocity of runner A? This time we got to take a look at a graph to help us out. Can we find the velocity at 2? Maybe? Okay, it's a little tricky, right? Because here's 2, and if you go up, we're somewhere right there. So can you tell me for certain, is it 6, is it 7, or is it something in between? You can't say for certainty, right? It depends on how straight you draw your lines, right? So somehow we should be able to figure out perhaps the equation of this little piece here and plug in 2. If it's a straight line, right? We can find the equation of a line. We need, I know, right? It's tricky. Y equals mx plus b. So the slope of this line, if we do rise over run, we went up 10 over 3. Y-intercept, 0. All right? So if we plug in 2, we'll get 20 over 3. So it's actually something in between 6 and 7.
6.6.
And it's velocity, so another meters per second. All right, so if you can't get it exactly, you may have to do a little figuring. Okay, write an equation to help you out. I know you can do that. Okay. All right, part B. Find the, same type of question, but this time acceleration. Acceleration, runner A, acceleration, runner B at time 2. Now they give us velocity information, so we have to think about how can we use velocity to help us get acceleration values. How are velocity and acceleration related to each other? Slope of velocity is acceleration. Okay, so we need, if we're looking at time 2, the acceleration at this point would be the slope of this line. Did we already say what that was? 10/3. Okay, basically the derivative of that equation that we found. Can we put a unit of measure on that? If it's acceleration? Meters per second squared. All right, now for runner B, we have an equation to go off of. So if we want the slope of velocity, in this case we're going to have to do a derivative to get our slope. We'll do this one by hand. Okay, we'll do our product rule. So we'll have low d high minus high d low, square the bottom, and we're good to go. All right, now we got to plug in 2. So 7 times 24 minus 48 times 2 all over 7 squared. Definitely need a calculator for that one. Let's see. 7 times 24. 1.469. You could be 3 if you chop it, or 4 if you round it. All right, so acceleration unit of measure, we'll have meters per second squared. If you had to do these on your own, do you think you'd do okay? To a point, at least? Some of them? Me too. I'm a little tired too. All right. Last one, okay? Last one. 2002. By the way, these particle motion problems are very popular. I'm almost going to guarantee you that there's at least one of them as a free response every year. Okay, so they're pretty important. Let's see. An object moves along an x-axis, so we're going left and right, with an initial position at 2. So if you think about the x-axis, you're not starting at the origin, you're actually starting 2 units to the right. The velocity of an object for time greater than 0 is given by this function. Is the acceleration, or what is the acceleration of the object at time 4? They give us velocity, we got to figure out acceleration. How do we do that? Derivative. Okay, so we'll say acceleration is the derivative of the function. Can we find a derivative shortcut to help us out? Chain. All right, derivative of outside. Keep the inside. Finish the chain by multiplying by the derivative of the inside. Pi over 3. All right, so we're going to plug in 4. We'll have cosine of 4 pi over 3 times pi over 3. Now, you may need your unit circle, okay, if this was a non-calculator question, which I bet it would be. You'd have to think about on the unit circle the cosine value of 4 pi over 3. 4 pi over 3 is in the third quadrant, so cosine would be negative, because x value is negative, and I think it's negative a half. So then this would be negative pi over 6. Did they give us units? I don't think so. All right, so in this case, we don't have to worry about it. Looks good. There's our acceleration. All right, let's check this out. Consider the following two statements. For some time, okay, anytime you want to pick, between 3 and 4.5, the velocity of the object is decreasing. For the same time interval, the speed of the object is decreasing. Are either or both of these statements correct? For each statement, provide a reason why it is or is not correct. Okay? How can we check to determine if velocity is decreasing? If velocity is decreasing, if it's going down, yeah?
Wouldn't that be opposite sign of acceleration?
So that's talking about speed. Okay, we'll get there in a second. If velocity is decreasing, the graph is going down. So if the graph is going down, the slope is negative. So the slope of velocity, aka acceleration, is negative. Okay, we got to check to see if acceleration is negative on that interval. What do you think? If you were to pick any number you wanted between 3 and 4.5 and plug it into acceleration, would we get a negative value? Do we already know acceleration at a number between 3 and 4.5? Yeah, right? Didn't we do that here at 4?
Yes, we do.
Right? And isn't acceleration negative? Yeah. Okay, so for, on this interval, if you were to pick any number you wanted, acceleration would be negative. Okay, so we'll say statement 1 true because a of 4 is negative from part A. All right, let's check out statement 2. For any point in time between 3 and 4.5, the speed of the object is decreasing. So if we want speed to decrease, if we want to slow down, what connection do we need? Position, velocity, acceleration, what's going on? Yeah?
Does velocity and acceleration need to have different signs?
Yes. So V of t and A of t have opposite signs. All right, so let's think about this. We already said that A of t is negative, okay, because we saw that in part A. How can we test to see if V of t is negative or positive? How can we see if it has an opposite sign or not? We know acceleration at 4 is negative. Can we somehow figure out the velocity at the same time? How can we figure out V of 4? Plug it in, right? They give us the velocity function. Now, we just really got to figure out is it positive or negative to help our case. So if we think about this, if we plug in 4 here, we'd have sine of 4 pi over 3. And in our unit circle, 4 pi over 3 is in the third quadrant. So is the sine value positive or negative? negative, right? Because sine is like a y coordinate. So v of t is negative because we'll say sine is negative in the third quadrant. I mean, you could actually calculate it out. You can get the decimal value, but either way, it should still work out. So if we are accelerating to the left, but also moving to the left, is the speed decreasing? You're moving and accelerating in the same direction, so you would speed up, right? So statement 2, we'll say false, because a of 4 and v of 4 have the same signs. So speed would increase. Is it starting to sink in? I'm hoping. Okay. We're going to do more with particle motion tomorrow, but we're going to take a look at a little bit more with position, like how we can figure out distance traveled. We've been doing a lot with velocity and acceleration, but we haven't really touched distance yet. So we'll check that out tomorrow.